Hello everyone. So in this video I'm going to demonstrate to you why a couple of these rules work for solving second order differential equations. Okay, it's not a proof, but it's just going to demonstrate to you why these solutions work. And what I'm going to do is I'm going to demonstrate why these ones, the real distinct and the real repeated roots, work as solutions to the second order differential equation. So in a previous video I've actually worked through this problem here. So if you want to see that, just go back to my previous video, otherwise just go with it. So in this one we worked through it and we got this as our general solution. Okay, so y equals that is the general solution of this. Now to prove that works, you need to start off with that and substitute into the original. So what I'm saying is this, I'm saying that this is our general solution. We need to find a way of checking that it works with this. So to do that, we can substitute y in there, but we need to find dy dx and d to y dx squared. So a bit of work needs to be done. So if y equals that, we differentiate to find dy dx. So differentiating each term at a time, this one will become that, and then this term will be that when you differentiate it. I'm sure you're happy with this. If you're understanding this second order differential equation stuff, you should understand simple differentiation. Okay, and then the second derivative, d to y dx squared. So differentiate that, you're going to get this, and differentiate that, you're going to get that. Okay? And then we just substitute these in. And that will prove to you that this must be the general solution. Okay, so we need to do 2 d to y dx squared, so double that line, which I've just written by here, and then plus 5 dy dx, so 5 times that one, so I've just written that by here, plus 3y, so 3 multiplied by that, which I've just written by here, and then you need to add these together and you should get 0. Let's just check that works. So these are the like terms, we add those together, so 3a can be written as 6 over 2a, so 6 over 2 plus 9 over 2 is 15 over 2, subtract 15 over 2, so those cancel. And then this one, it's a bit easier, isn't it? 2 plus 3 is 5, subtract 5, 0, so all that gives you 0. And because it does give you 0, that is a proof that this must be a general solution to the equation. Okay, I'm going to do the repeated roots one next. So again, in the early video, I went through this, explaining why that was the method. And this was the general solution. If you're happy to just go with this, to demonstrate why this works, I'm going to substitute that back into this. I'm going to do exactly the same thing. Okay? So that is, for this second order differential equation, if this is a solution, we need to substitute that back in there, find dy dx, find d to y dx squared, and substitute it. Now to differentiate this one, I find it easier just to expand the brackets first. You don't have to, but I'm going to. Okay, so expand the brackets, you get that. And then differentiating this, so dy dx, so the first term is just going to be that, and then the second term, you are going to have to use the product rule for that. Okay, the product rule, v du dx plus u dv dx. So using the product rule, so e to the 3x times the derivative of bx, which is just b, so that would be b e to 3x, plus, and then bx times the derivative of e to the 3x, so bx times 3 e to the 3x, which is just going to be that. Okay. And then next we need to differentiate again. We need to find d to y dx squared. So this term, so that's just going to be this here. This term is going to be this here, but then this one, you have to use the product rule again for it, because you've got an x term multiplied by e to the 3x. So this time, u will be 3dx, v will be e to the 3x, so v du dx e to the 3x times derivative of 3dx, which is 3d. So there we go. And then u, which is 3dx times derivative of e to 3x, so 3 times e to 3x times 3dx, which is that. And that can simplify a little bit. Okay, so notice those two like terms, you can combine them to make it 6. So I've got my dy dx, my d to y dx squared. In summary, we've got y, dy dx, d to y dx squared. This was the second order differential equation. We substitute in and check that it gives you 0. So I'm going to do that right now. So first of all, d to y dx squared, which is just that. Negative 6 dy dx, so negative 6 multiplied by this, which gives you that. 9 multiplied by y, which gives you that. And then just check. So I've done it so that you've got the like terms underneath each other. So these are the like terms. 9, 9, negative 18, 0. 6, negative 6, 0. And then this one, 9, 9, negative 18, also 0. All checks out. So it gives you 0. Okay. So just going back to this. So that's a demonstration for you as to why the solutions I've got for those type scenarios give you are the actual solutions to the differential equation. You could do the same for those two. I'll leave that as a challenge for you to work out. All you do is just work through it and then just demonstrate that by finding dy dx, dt y dx squared and substituting back in. They must be the solutions. Now that's not a proof, that's not a general proof of why these work. For a general proof of why these work, you'd have to work from scratch for that. That's a bit more difficult. This is just more of a demonstration video showing you why this process is working for you. I'm hoping you found that interesting and helpful. Thanks for watching and I'll see you again.